This is the lecture for Module 4 of Unit 5. This lecture is on buffers. A buffer is a mixture which doesn't change its pH much when an acid or base is added. Now, buffers can be made by chemists for experimental work they're doing if they want to fix the pH, or you will read about or see naturally occurring buffers in this course. The principal components of a buffer are a weak acid and its conjugate base. So, acetic acid and acetate is a typical example of a laboratory buffer. The idea is the weak acid, acetic acid, in its molecular form will react with any base added. The acetate ion present will react with any acid present. All right, as an exercise, let's consider a buffer solution made of 0.3 molar acetic acid and 0.4 molar acetate, these two concentrations together in the same mixture. Let's begin by finding the pH of this buffer solution. Alright, as it turns out, you can use Ka or Kb for the conjugate base to build a nice table and solve this problem and get the same answer. We will look at this from the standpoint of acetic acid. And remember that the reaction in this case is acetic acid gives up its proton to form H plus and acetate. Ka has the ions in the concentrations in the numerator and the neutral concentration in the denominator, and we have seen before that this number is 1.8 times 10 to the minus 5. Alright, now our idealized beginning is we have 0.3 molar acetic acid and 0.4 molar acetate, and no dissociation reaction going on. So our hypothetical ideal state has no proton, 0.4 moles of acetate, 0.3 moles of acetic acid. H plus and acetate must increase by X. Acetic acid concentration must decrease by X. And hence we have these equilibrium quantities. Alright, we will anticipate, especially since we have this conjugate base present to act to force this equilibrium to the left, we will anticipate that H plus is small compared to these concentrations, which means when we write down Ka, we plug in 0.4 and 0.3 for acetate and acetic acid concentrations, solve for X, and obtain a proton concentration which we can rapidly convert to a pH. 4.85 is the pH of this buffer. Alright, okay, let's reconsider that. We just wrote down Ka for acetic acid and the number, and H plus multiplied by the ratio of conjugate base to acid concentrations. Alright, what we just essentially did on the last slide is rearrange this equation to solve for H plus. And when we do that, we get the concentration on the previous slide. Another way of approaching this problem, you will often see, especially in biochemistry, is taking the negative log of both sides. In this case, negative log of H plus is negative log times K times acid concentration over base concentration. We can separate terms on the right hand side. That's negative log Ka and negative log of the acid to base ratio. Carry down to the next line, what I have done from this step to this step is take the reciprocal of the expression in the natural log, which changes its sign. Alright, this gives us, since the negative log of H plus is the pH, and the negative log of Ka is the pKa, this gives us pH equals pKa plus log of the base concentration over the acid concentration. In general, you will see if you want to calculate H plus for a buffer, H plus can quickly be calculated as Ka times HA over conjugate base concentration. You'll see that expression here. Or you could take the negative log of this equation and arrive at pH equals pKa plus log of A over HA. Note that when you use this equation, the place of A and HA in the numerator and denominator has flipped. Alright, now to illustrate how a buffer works, or the change in pH. Assume 5 milliliters of 1 molar hydrochloric acid are added to 100 milliliters of the previous buffer. What is the change in pH? Alright, remember our original pH is 4.85. Alright, we have 100 milliliters of this buffer, so we can calculate moles of acetate, 0.04, and moles of the conjugate acid, acetic acid, and that's 0.03. Meanwhile, we've added 0.5 thousandths of a liter of 1 molar acetic acid and have added 0.005 moles H+. The acid we have added reacts with the conjugate base. Right. H plus and acetate react to make acetic acid. This uses up 0.05 moles of acetate and produces 0.05 moles of acetic acid. We assume this reaction goes all the way in this case. A good approximation because we know K for the reverse reaction is small. Alright. Right. We know change in moles of acetate, so we can calculate new moles of acetate. That's gone down. Meanwhile, moles of acetic acid has increased. And we add that to the original moles of acetic acid. We find that in this case, we have 0.035 moles of each. Alright, we've added an acid, which means we anticipate that the pH will go down. Now let's see how far down it goes. Alright, here we build a nice table for the changed buffer. Notice that what I have here, instead of concentrations of these two species, we have moles, or I have written moles. And I talk about the change in these concentrations in terms of moles, and I write the equilibrium concentrations of these species in terms of moles. You can think of this original column, row, the one for H+, as being in moles as well. Right. Essentially what happens when we introduce, when we get to the point of solving for H+, well, X, concentration of H+, is equal to 1.8 times 10 to the negative 5. And the pH is the negative log of 1.8 times 10 to the negative 5, or 4.74. We could apply the Henderson-Hasselbalch equation as well. pH on the left-hand side. Take the negative log of 1.8 times 10 to the negative 5, and that's our pKa. Then take the log of 0.035 over 0.035. This goes to 0, by the way. And the pH is 4.74. Right, so we can put these moles, not molarities, either in this expression or in the Henderson-Hasselbalch expression to determine the pH. Again, our ice table here uses moles of buffer, not molarities. Since the volumes of the two components are the same, they're both in the same volume of mixture, neglect of volume cancels out. That's why I'm able to do this. All right. Our change in pH is 4.74 minus 4.85. Notice our pH has gone down, but it has gone down very little, negative 0.11. This is a small change. For comparison, if 5 milliliter 1 molar hydrochloric acid were added to 100 milliliters of water, not buffer, the pH of the water would go from 7, neutral, to an 105 milliliter solution with a pH of 1.3. There's a drastic pH change on addition of the acid. Alright, I've asserted here you can use moles in this ice table and in the equilibrium expression instead of molarities. This last slide just illustrates or re-illustrates that principle. Pardon technical difficulties. Alright, here is a traditional ice table for the same problem. We're looking at it in which the rho for H plus remains unchanged, but instead of moles in the other two rules, I divide these moles by the new volume. Remember, it's now 105 milliliters to obtain the new molarities. Alright, and you notice we have the same pattern of plus and minus x as before. 1.8 times 10 to the negative 5 is H plus, what we're solving for, times 0.035 divided by 0.105 times 0.035 divided by 0.105. In other words, when we divide moles by volume in the numerator and in the denominator, volume cancels out. So we don't have to worry about neglect of volume when we recalculate the pH after addition of acid to a buffer. Again, we find a pH of 4.74 and the same pH, small change for this buffer. Alright, you will see ratios of moles used instead of ratios of molarities and other examples of buffer calculations. That concludes this presentation on buffers.